Okay, yeah, so Simon Maskell from University of Liverpool. People on the right-hand side of my name are the people that have done all the hard work, so they should take all the credit. Anything that's wrong is my fault. I talk a little bit about the motivation. So let me just move this over here so I can see it. Motivation and kind of the vision. Talk about the specific tool chain that we've developed, and show you some results and conclusions. I should have introduced the title. So what we want to do is run lots of, relatively speaking, short chains. Okay? And we want to capitalize on the big computers that are kicking about, that these deep learning people that you've probably met are using a lot, to our advantage as people that don't traditionally make use of those big computers. That's what I want to do. Okay? So I'm just going to kind of describe MCMC primarily for the kind of more developer kind of subset of the audience to hopefully understand a couple of things which I think are kind of interesting. So MCMC used extensively in Stan, but also other things like PyMC3 and kind of NumPyro. It works by drawing a sample from nuts in lots of cases from a proposal distribution and accepting that sample, kind of, with a probability that's the minimum of 1 and a thing we'll call A. And A is the ratio of, is this going to give me a, no? A ratio of a target distribution pi divided by another target distribution. Go back one slide, thank you. Thank you. Thanks, Charles. A target distribution pi divided by pi evaluated at where you were before, a proposal distribution Q going backwards and a proposal distribution going forwards. Two things I want you to note are coloured non-black. Okay? The blue bit, the letter Q, and the brown bit, the letter K. Okay? Remember the rest, but beyond that you don't need to worry. I may talk about two things. One I'll call burn-in, which is how long it takes to generate samples that you're going to then throw away and use the ones that are left, and how long it takes you to do the hyperparameter optimization, estimate the mass matrix and so on. So I refer to burn-in and warm-up. Hopefully I'm using the same terminology as other people. I have experience of having very computationally expensive models that were less complicated than the models I really wanted to use. Yep. And I had to compromise those models to get them to give me answers in the time I wanted to use them where I wanted to use them. A specific example would be for COVID, for the UK government. And I feel that there are other people interested in this many-chain regime. Worth saying there are lots of other people who contributed to UK COVID, obviously, probably many of them in the room. There's another thing, okay? There's another thing called an SMC sampler. And an SMC sampler calculates an importance weight rather than an acceptance ratio, okay? And when it does that, it calculates the ratio of pi over pi times L over Q. Now remember I tried to get you to remember two things? There was a blue bit of text, go back, which was a Q, which is now an L, and L and Q are different letters of the alphabet. Yep. And there was a thing that was K, which has now changed in brown, which has now changed to K minus 1. The rest of it's kind of the same, except there are these I's in brackets. Yeah? So the I's in brackets mean that you're doing this in parallel. So this is a numerical Bayesian inference algorithm that is designed to run in parallel with lots and lots of chains indexed by I. It also has the property that it looks a bit like MCMC's acceptance ratio, except you can choose L to be anything you like, doesn't have to be Q. And it turns out the optimal L is not Q. And you don't have to have pi being the same well, you have to pi k on the bottom, which turns out to give you another design degree of freedom, if you like, in terms of how an SMC sampler is configured. However, if we make the proposal an MCMC kernel, so conceptually we stick MCMC inside the SMC sampler, and if we make an assumption about what this L thing is, it turns out you do a bit of maths and you end up with multiple chains running in parallel, not interacting with one another, all doing MCMC. Okay? So a slightly weird configuration of an SMC sampler is exactly running multi-chain MCMC, and it's a suboptimal SMC sampler. Okay? So the sales pitch, the vision, is around SMC samplers don't have to be configured to be exactly many short chain MCMC. We can change the target over time. So if you want to do things like tempering, that's completely fine. Come on, it's fine. We can use other proposal distributions, so we can free ourselves from accept reject if we so wish. And we can use other L kernels which turn out to have the property that we can get better improvements from parallelism and not have burn-in holding us back. So I'm excited about this. Hopefully that comes through. And we perceive, sorry, I'm conscious I'm giving you feedback, we perceive it's likely that SMC samplers can be configured to outperform many independent MCMC chains. Yeah? I'm not going to argue that today. I'm instead going to take a slightly more, less ambitious kind of view, which is that we want to start with many chain MCMC and see what we can do. Yeah? So the vision is not many chain MCMC, but let's do many chain MCMC first. So what we actually did is we dug into the back end of Stan, tried to change it to use MPI to run multiple chains in parallel across multiple computers, got that to work, got it to scale, happy days. We then tried to do the same thing with OpenMP, another bit of kind of software, to enable us to offload onto GPUs, and we really couldn't get that to work. And I, to this day, do not understand why. So we gave up. What we did is we then reverted to a different tool chain to the one that we wanted to use. So what I'm going to talk to you about is what that different tool chain is. So, turns out some clever people, also very friendly and helpful, in IBM research, have made a transpiler that takes your Stan file and turns it into NumPyro code. Yeah? That exists. It's on the internet, download it. And in theory, that lets you do everything that you can do with a NumPyro code now with something that's exactly equivalent to your Stan file. Except it's not being actively maintained, it's not tested on GPUs, and uses deprecated versions of JAX and NumPyro, which basically means doesn't work. And it also is incompatible with anything you'd want to do. So, you probably get the idea, I'm not an IBM salesman. However, what they've done is rather neat. So what we've made is something that uses their stuff, but writes a little bit of post-processing in Python, because we can write Python and we find OCaml completely incomprehensible. And it removes the redundant JAX and NumPyro code, ensures that we can do things on the syntax and makes sure everything works, fundamentally. So we fixed it. Yep. And added some support for some exemplar bits of stuff that we couldn't find in JAX and needed. There's a gotcha, which is about how do we do step size selection and mass matrix selection, given that we've got lots of chains running in parallel. And so what we've tried to do is to mimic the logic of what Stan does, but do it by averaging across the many chains. So rather than estimating a covariance matrix or covariances along a chain, we estimate it across the chains. Yeah? And rather than trying to estimate what a good step size is along a chain, we try to do that across multiple chains. It's a bit clunky. We locally, it's being recorded, maybe I shouldn't say that. We have a name for this approach that we use locally that's not enormously flattering about it, but it does have the advantage that it exists. Yeah. So we have an IBM well-written bit of code, some post-processing that we have written that enables us to use it, and some stuff that enables us to hopefully get good mass matrices and step sizes out. So what happens? So we threw it at posterior DB, 120 models. Not totally true. We threw it at posterior DB, we were horrified at what happened, and then we changed it, and then we've gone around that loop a few times, and we ended up today with about 70% of them being of the models that are in posterior DB being supported by the toolchain that we have. So not 100%, and I'm worried that if you came up to me with a new model, I'm not confident that we would be able to do it with 70% probability because we're massively biased by the specifics that we were looking at. The biggest error comes because some of the functions in Stan output a data type that then gets fed into another function that expects a data type, and in JAX those two things are different. So it's a bit like outputting a string of one character and then feeding it into something that expects a character, and it says, what's that? So we can fix those, but we haven't. We're actually not using nuts at the moment. We want to, we know how to do it, we just haven't got it to work yet. We got a big computer with a nice big graphics card. We're comparing with BridgeStan running things in parallel to understand what pain we get from changing to JAX rather than Stan, and we're going to focus a bit on ARMA as an example. If you change so imagine you want to do, I think, 2048 iterations. You could do that with draws. You could do that by having one chain running for a long time, or larger numbers of chains running for shorter times. It turns out that with the configuration we have at the moment, because we're doing parallel MCMC and not an SMC sampler properly, it hurts us to run things with many short chains relative to a smaller number of longer chains. If we look at the run time, JAX with a CPU is really quite slow relative to BridgeStan, but the GPU version of JAX is faster than we can get BridgeStan to run, and I totally accept you might be able to get it to run faster than that. But the interesting bit I would suggest is here. So we at the moment, sorry, do you want to go back, Bob? And again, the crossover point happens, depending on what you consider the baseline to be, around about 600 or 1,000 parallel chains. It starts becoming worth using the GPU in the current code base as it stands. We would want to improve that, but today that's what I can report. We can run Stan in parallel in the many short chain regime on a GPU. The post-processing tool lets the IBM stuff work for most of the models, but not all in there. BridgeStan, at least for ARMA on a CPU, is faster. That's probably not surprising, I would expect. Our transpiled JAX code is 5 times slower than BridgeStan. Our many-cored GPU outperforms a moderately cored i7 for about 1,000 chains, and it's about 5 times faster if you go up. So 5 times faster than BridgeStan, actually, if you go up for lots of chains. We can benefit from doing things with SMC samplers. So what should we do next? We should optimize the tool chain by looking at more models, optimizing our implementation, running things across multiple GPUs, extending the library to support the additional things that we can't currently cater for, which include ODEs, which is infuriating, and figure out why we can't get this to work in the back end of Stan. We should also improve the inference algorithm, so ditch many-chain MCMC and use something that we're happier with, and replace the variable step HMC with something that's a bit more competitive. And then I suppose the real point is I don't want to accidentally generate a competitor to Stan, which I kind of feel is a possible way this could go out, and I really don't want to do that. But I do want to generate an open source library that people can benefit from, and I'm really keen to understand could this be useful to you? So if you have views on how we should take this forward from a development angle, or views as to how it could be useful as a user, I'll be really keen to hear from you. Thank you very much.
So we have time for a few questions, and in the meantime, the next speaker is set up.
Really cool. I have a question. In terms of runtime, you check the time in seconds, right? It was a bit quick for me to see the runtime.
Yes.
Did you I don't know, compare something like effective sample size per second or something? Because I don't know the differential efficiency of these different algorithms, or what efficiency we may lose through maybe short.
Yeah, so just let me. So the intent is that for the same random number sequence, all the different implementations would give the same output, but there is a difference in terms of if you run 200 chains for 10 iterations versus 10 chains for 200 iterations, that would give you a different answer. And go on.
Question is you talked about warm-up at the start. How have you handled the warm-up in the different implementations?
So I was conscious I was needing to speed up, so I glossed over that. So we across the chains, we implement the same sequence of steps that we understand Stan to use, whereby you iteratively estimate a mass matrix and estimate a step size and estimate a maturation. So, but we do that attempting to combine the information in the samples across the chains, and we are not convinced we're doing that optimally. Yeah. Go on, Bob.
So I think there may be something wrong with your evaluation.
Okay.
I was expecting Charles to ask this question, but I will ask it for him.
Yeah.
Which is that when you have 512 chains of length 4, shouldn't you have at least an effective sample size of 512? But you were showing a factor of 10 to the 2 difference in error, which corresponds to like a 10 to the 4 difference in effective sample size. I just don't see how those results are possible that you showed us. So are you starting each of the parallel chains at the same point after warm-up, for instance? That would account for what we saw.
I didn't think so. I don't know.
Because if you start those 500 chains
Yes, yeah.
as independent samples after warm-up, then you should have an effective sample
Yeah.
size of at least 500.
I don't think that's true, because I mean, if you sample the initial points on -1, 1 with a uniform distribution or whatever Stan is using, then you're still initializing them in a similar region, right? Depending on the model, that might very much be like initializing them at the same point.
But this has already gone through warm-up, right? So we should have, either we haven't run warm-up long enough and forgotten our initialization state.
Yeah.
Which
Yeah, maybe true. Yeah. So
once we've warmed up, we should have independent chains, right? Anyway, we can take this.
Yeah.
offline.
So
I'm
no.
confusing
So
everybody, so
yeah.
Let's look at the slides.
Yep.
Thank you.
Let's start.
Yeah.
Thank you very much.